drying sequence will cause cracking, shrinkage cracking, which you will think, oh my God, my pore structure was so good. That is one reason why, have you heard of people saying, oh, I had fly ash in my concrete and it has a lot of drying shrinkage? What does fly ash do? Makes the size of pores, pore size refinement, makes the pore size of pores small. When water goes out of the small pores, stresses are going to be higher. Therefore, you will see silica fume. Have you heard of shrinkage in silica fume? Everybody will say that except the silica fume guys, right? Of course, I mean they'll say that, they'll say yes, it shrinks but it won't crack. They're very smart. It shrinks, which is kind of true, because I've given you with silica fume a higher strength for your material. Therefore, even if you have shrinkage, it won't crack. And it's very hard to refute the fact that a high surface area material like silica fume does not shrink. Right? When you have a large surface area, you have large area for water to evaporate. Therefore, it should shrink. It will shrink. But if it shrinks, they'll say, oh, it doesn't crack much because our strength is better. Might be true sometimes. And again, you can't make. That's why when some of you ask me, what will happen, sir? I said, I don't know. You can't make generalized statements about, classic example again. Father behavior, I know. Mother behavior, I know. Can I predict the son's behavior? Same thing. Right? I know one concrete in one place, another concrete in another place, same concrete some other place. I have absolutely no way to predict. Right? So these are all, there are so many things, so many variables that go along. So try to understand and then try to come up with your own rational arguments. Okay, and then there is physically adsorbed water, which will go when the relative humidity goes further down. Gel water, we really don't want to speak of gel water leaving, because CSH, that gel water is the H in CSH. If that H goes, it will become CS. You don't want to talk about a calcium silicate scenario. You want the calcium silicate hydrate. If it's calcium silicate, it's just a mushy powder, it will just go away. You want that hydrate H to be. So some people will talk about, oh, removing gel water. I'm not a big fan of talking about removing gel water, because if you remove gel water, you don't even have the thing in the primary place. So yeah, you can remove capillary water, you can remove adsorbed water, you can rearrange gel water. So gel water changes, like I said, because this capillary water is gone, you have internal rearrangement. So gel water rearrangement happens, gel water doesn't go away, should not go away. And even concrete textbooks, you will see gel pores are dry, drying of gel pores. I mean, gel pores should not be dried. Okay, interlayer water has to be there. If your argument that gel pore, I'm just calling it a gel pore because I'm calling the smallest pore gel pore, I'm okay with it. But if you're calling gel pore as the interlayer water, that's not correct. Get it? Okay, so here are the 1, 2, 3, 4 and 5 from the previous picture. So now you have to put these together. Okay, so 1, what was 1? Very early loss of water, right? At even a small drop in RH. 2 here, these parts where you will have lot of water that will be gone from in the big zone until about 40-45% RH. 3 and 4 are generally the adsorbed water areas. Okay, and I have deliberately, this 4 is misplaced, I should not be calling, this 4 is probably this pore water which doesn't have an axis. Gel water really doesn't go away. Okay, now have you seen how a water molecule looks like? It's like a Mickey Mouse, right? Oxygen with 2 years, hydrogen with 2 years. So we call it the Mickey Mouse representation of water. So OH, 2H and the O. If you look at the scale of pore sizes, now remember the scale of pore sizes, right? If the gel pore is my size, the capillary pore is the size of Mars. So you have all these size scales that it has to transcend. Therefore, it's natural that not one mechanism can explain everything. Right? You are trying to a lot of people have done this, tried the unified mechanism of shrinkage. Nonsense. You can't explain, it's like a string theory for universe. You can't. There is no one mechanism that explains everything. So we do it typically by 3 phenomena, and the reason why I do only these 3 phenomena is these are very easy 3 phenomena for you to remember what happens. And therefore, when you see a shrinkage cracking, you can relate to it very quickly. Okay? The first is the capillary stress mechanism. Second is a disjoining pressure. Third is the surface energy changes. I'll explain to you very simply. capillary stress mechanism happens only at a higher RH. Which means, remember, water from capillary pores will go away. Remember the stage 2 that ends at about 45% RH in that picture? Capillary water will go only until about 45% RH. So you really don't worry about anything else until then. Capillary stress. Water is influenced by pore walls. Very simple. You see this meniscus? Right? When water goes away, the pore walls try to shrink. This is a larger pore, this is a smaller pore. Larger pore at 100% RH, this pore dries off. If the RH starts to go down, smaller and smaller pores dry off. Okay? So water can be lost only by creating an air-water interface. Water cannot be removed by evaporation unless RH is lowered. I gave you an example of your clothes drying, right? Water cannot be evaporated unless RH is lowered, which means when it is dry, when it is raining very heavily, its relative humidity is very high, you cannot try to put a cloth right next to the rain. It doesn't have to be in the rain, but right next to the rain and close relative humidity and try to heat it up. It's not going to dry. What you need is not heat. What you need is removal of RH. If the heat removes RH, fair enough. Okay? So whatever mechanism that drops the RH is what you want. Very similar idea here. Water, and then in that case, water can be lost only by creating an air-water interface. So if you talk about drying of anything, the first principle in drying is creating an interface between air and water. Water, 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 water everywhere, 100% RH. You take one water molecule away, create a water-air interface for that air to drop the RH of the whole system. Then you take another water molecule away. You see that? Heat does that typically, right? Gradually takes water molecules away, gradually evaporates the water molecules and then creates space for air, first as water vapor and then as air molecules. That's what you do. So water can only be lost by creating an air-water interface. That's a capillary stress theory. So basically you have hydrating cement, you have water in the pores, capillary stress, you dry the water off, and then the simple equation, capillary pressure or capillary stress is 2 times surface tension over the radius. Again, pressure inversely proportional to the radius. It can also be given as the natural logarithm of the relative humidity divided by a constant K. I have told you where this is happening in that curve, right? In the stage 1 and 2. Capillary stress very early on. This shrinkage is popular in most parts of India where there is reasonable amount of rain. Forget Rajasthan, forget very dry areas, because you will never drop really lower than 45% RH, because you have seasonal rains replenishing water in your concrete all the time. So this mechanism, if you have drying shrinkage, it is this capillary stress mechanism that happens. The next one, disjoining pressure also happens at greater than 45% RH, but disjoining pressure is a readjust. I told you that because of capillaries, water going out of capillaries, you will have some local readjustment, right? Water goes out of capillaries at what RH? Greater than 45. But when that happens, at that same RH greater than 45, there is some readjustments, internal readjustment. That internal readjustment is the disjoining pressure, because the adsorbed water, because of van der Waals attraction between the layers, you start to lose the adsorbed water, resulting in a net volume decrease. So then you have van der Waals attraction dominating between those two layers, because this adsorbed water is gone, readjusting because the environment around that gel is now drier. Okay? So that's disjoining pressure. Again, everything in the microstructure. Surface energy happens at less than 4. This is the only thing that happens at less than 45% RH. Very difficult mechanism to explain theoretically, but I'll do the practical stuff here. Capillary and disjoining pressure at lower RH is not even existent, because capillary pores have no water. Disjoining pores are also not there because the equilibrium has been attained. Then you have to remove the strongly adsorbed water. Now, if I have a layer of something and I attach something on that layer very strongly, okay, the surface energy of that layer is very high. I have attached, so think about, I don't know what is a good example. Whatever, think about a piece of cloth and I'm attaching small beads in that cloth. Okay? To remove that, because of the surface area, to remove the bead is going to be very hard if there is a kind of a natural attraction between the cloth and the bead. It's going to be very hard to remove that. So removing the strongly absorbed water increases the surface energy of the solid. So you will have, when I remove a layer of water, you remember BET theory, nitrogen forming on the surface of layers, right? So when you start to remove that, you have to overcome the surface energy of the solid. Okay? So when you do that, you will have, okay, where you will have a lot of pressure that is created, and that happens at low RH, and that is what happens. You really don't, unless it's very, very dry. So where I am in Phoenix, we have a lot of surface energy effects, but most places with reasonable amount of moisture saturation, capillary and disjoining pressure is enough to talk about shrinkage. Now, yeah, so the consequence is that, okay, so 2 or 3 different things. The consequence is that you will have cracking, very fine microcracks. You will have extremely fine microcracks because this is happening at a real small pores. You will have extremely fine. So the concrete will be extremely microcracked because of heat. Won't be visible. No, these are at a very small level. But it has a tendency, it will have the capacity under load, under constant fatigue, all these cracks will grow. So see, shrinkage cracks by themselves are not dangerous, unless it's a very large shrinkage crack that happened on the surface, right? Not very dangerous. None of the shrinkage cracks are consequent in terms of load carrying capacity. There has never been a case where just because of shrinkage the concrete failed. You have a crack or you have a series of cracks because of shrinkage, and then you have other mechanical loads on the structure. If you are on a road or a bridge, you drive through. If you are on a building, you have superimposed loads. These loads start to exacerbate and enhance the micro cracks, and those cracks will widen and fade. Okay, so here is the restraint ring test that I talked about. You have a steel inside ring, steel outside ring. You cast the concrete in between. You have strain gauges all over, and you measure the residual stress as a function of time. Residual stress goes up. Suddenly, when you see the stress coming down, that's an indication of cracking, right? That's a time of cracking. That's a stress of cracking. We can say 4 megapascal was the tensile stress of that concrete. Therefore, it cracked at 4 megapascal. This concrete, I threw in some shrinkage reducing admixtures. It's going on forever. It's not cracking. Okay, so the simplistic idea is you have a calculated tensile stress, specimen stress, stress based on Hooke's law, stress relaxation. All these, if you're doing a restraint ring test, ASTM standard tells you how to do all of those. Autogenous shrinkage, self-desiccation, internal drying, low water cement ratio, we talked about that, drop in internal RH. Chemical shrinkage, lower volume of hydrates than cement and water. Self-desiccation is reduction pore water due to hydration. So all of these are, you see this, sometimes this is, I feel this, sometimes this is overkilling using words. There are so many words: self-desiccation, autogenous shrinkage, chemical shrinkage, internal dehydration. A lot of times you use all of these different words and people get confused. It's broadly similar to what you guys heard yesterday when he was talking about the different journals and stuff, right? H index, I index, SCI expanded. At the end of the day, none of this matters. Right? You have to do your work, you have to publish in a good journal. But sometimes you do overkill with these words, and that is one of the downsides of research. I should say the downside also. I said a lot of positives, right? Because a lot of us, I want to be general, I don't want to include anybody in specific. A lot of us do research for the sake of doing research, right? I want a PhD, therefore I do. What's the use of it? Why do I care? I get my degree, right? So when you do that, that's a result. I want to develop something new. That new complicated everybody else. The world was a wonderful place without you. and your theory. Suddenly you came in, published a paper, and people started looking after this. So some people really, start low water cement ratio, yes. Autogenous shrinkage, yeah. Chemical shrinkage, every concrete, every reaction, every damn thing that you react one with the other has a chemical shrinkage. Really, does it influence? Depends. So be careful when you have all these terms. Be careful when you parse these terms, so that don't use the terms for the sake of using if you don't need it. For example, if you're doing volume changes in concrete, if you're doing everything in a perspective of cracking in a concrete bridge deck or a concrete pavement, forget autogenous shrinkage, forget chemical shrinkage. You'll be better off with drying shrinkage by itself. If you have materials that react very differently in a system, right? You have materials that really have expansion that's happening in the system very early on, then you talk about chemical shrinkage. If you use a very low water cement ratio concrete to get ultra high performance concrete, then talk about autogenous shrinkage. Use it for the right context. Don't take a 0.4 OPC standard concrete and start testing all of these. You wouldn't need it. You wouldn't know any difference. Context becomes very important. Okay? And shrinkage is one of the most important concerns that people have, and one of the still unconquered areas in the science of concrete. We still shrinkage and creep. We still struggle to understand the real mechanisms and the real ramifications of these things. Eventually we know it results in cracking, because if it doesn't crack, if volume changes and if it doesn't crack, nobody has a problem, right? It's only because cracking happens that we are concerned about it. And I think I have a slide on, okay, here is how you do autogenous shrinkage. So the other problem with your the other advantage with your ring test is the residual stress that you measure in a ring test includes autogenous, chemical, everything, because you start measuring as soon as you pour your concrete. But if you're doing your shrinkage, restrained shrinkage or free shrinkage bar, when do you start measuring it? After 24 hours, which means you completely lose that part. You completely lose that shrinkage, and you're getting only, this is your measured shrinkage, and then you're basing everything of that, and people put in these random numbers. 600 microstrains and the concrete will crack. Have you heard of that? You see that specifications written 600 microstrains and the concrete will crack. How do you know? 600 microstrains under what condition? Right? So again, sometimes we overkill, and somebody tells a number, and you might see it in US or Europe, somebody have done it and use this value, and immediately you put in the specifications. That 600 microstrains is very highly dependent on the RH. You don't have the same weather conditions as in another place. So a lot of those things will change. Shrinkage reducing admixtures can reduce shrinkage. Very simple again. A lot of companies are making shrinkage reducing admixtures, but if you can buy alcohol cheap, that's the best shrinkage reducing agent. Okay, alcohol. Basically, best shrinkage reducing admixture is vodka. Why? Russians drink more purer alcohol, right? In vodka, you normally know, right? Vodka alcohol content is much higher compared to the other Scottish and Irish drinks that you have. Again, of course, those are very expensive. You don't need that. So basically, it's an alcohol. Basically, it's an alcohol, higher alcohol content. What it does is a very simple thing. You know what is surface tension of water? Anybody know out of the top of their head? No? Surface tension of water? PhD students should know this number. But I still remember the old British units, 72 dynes per centimeter. So you can convert it to newtons per meter, whichever way you have. So that is surface tension of water. And remember, capillary pressure equation which I showed you earlier. Does anybody remember it without looking at it? P is equal to 2 gamma over R. What is gamma? Surface tension. So to reduce the pressure, I have two options. What are they? Increase the radius or decrease the surface tension. Increasing the radius meaning putting in large pores in concrete. Do you want it? No. Small pores in concrete, I like it, but small pores in concrete will give me higher stresses when water evaporates. So my option then is to reduce the surface tension of water. These alcohols do nothing but reduce the surface tension of water. You mix alcohol and water, what is the characteristic feature of mixing alcohol and water? These are totally miscible liquids. This is the example that you use in your basic undergraduate class, chemistry class, miscible fluids and immiscible fluids, water and oil, water and salt, water and sugar, water and alcohol, right? Completely soluble, totally miscible fluids, water and alcohol, which means once you mix them, you have very homogeneous distribution throughout. The molecules, both of the molecules like each other so well that they distribute very uniformly so that you drop the overall surface tension. Dropping the overall surface tension means dropping the overall pressure. Dropping the overall stress meaning reducing the chances of cracking. That's a simple way in which SRAs work. Okay, so I think we'll have time to finish creep and viscoelasticity also today. Quickly, again, we talked about viscosity being the resistance to flow under stress. Again, I'm doing only those properties that are relevant to microstructure or using it with microstructural relevance. So you have combination of viscous and elastic properties. All of you know what creep is, right? Creep and relaxation. Okay. Concrete has solid-like characteristics like elasticity, strength, stability. They also have liquid-like characteristics like flow. Rheology, we talked about that. So materials that demonstrate both viscous and elastic nature are called viscoelastic. Creep is the increase in strain under constant stress. Relaxation is drop in stress under constant strain. Okay, so we need both of these. So let me ask you a question. If you are building a high-rise building with concrete, columns with concrete, there is a natural tendency to go to high-strength concrete, right? If you're doing a very high-rise structure, very high-strength column. What is the reason that they give for a very high-strength concrete for a column? You can reduce the member size, right? So high strength, you can reduce the member size. But what happens with a very high-strength concrete with respect to elastic modulus? Elastic modulus is a function of square root of the strength, right? So what happens when the strength goes up? Elastic modulus goes up. What happens when the elastic modulus goes up? Think simple linear elasticity. Stress is elastic modulus times strain. For the same strain, what happens when elastic modulus goes up? Stress goes up. What happens when stress goes up? You are likely to have microcracking. What is the only thing that can save you from this higher stress? Relaxation, right? What you want for relaxation? A lower elastic modulus, right? Very stiff materials don't relax. Want a lower elastic modulus for relaxed stresses. Now look at the paradox. Immediate gain, reducing cross-sectional area, giving more plinth area to the builder and developer so that he can sell more square feet of space. High strength is a very fancy term that everybody loves. Great high strength concrete, wonderful. Look at the chances of cracking in those concretes, right? This is common in the US with very high strength bridge decks that they do. So high strength, high performance bridge decks. When you have high performance bridge decks, you invariably have cracking because higher strength concrete does not relax well enough. Stresses don't relax. When you have stress, this is like somebody who will not cry, keep holding on to stress, and finally when they break, they just break down completely. So you have very high stress, can't relax, they fail. Over the last few years, they reduce the strength requirement for bridge decks. Unless it's an ultra high performance concrete with 2-3% fibers, that's a different story. Now when you have fibers, the whole thing changes, right? When you have steel fibers, the whole mechanism changes, the stress transfer, the pull outs, the elongate, all of those change. So that's a different story. But for normal concretes, they drop the strength. They said we don't need high strength bridges. What we need are crack free bridges, because what happens in the US, most places have snow. And if you have bridge, you automatically put in sodium chloride to melt the snow. And when sodium chloride is put on top of a bridge deck and you do that for 3 or 4 months in a year, you're very likely to have a high chloride content.